Today we present BlendCLIP, bridging synthetic and real domains for zero-shot 3D object classification with multimodal pre-training. At the center of our problem is open vocabulary, open perception in 3 dimensions. What does it mean exactly? A model that can handle classes or labels that it has not seen during training before. And this could be relevant for us for zero-shot classification of objects, where we want to classify those that had not been seen before at all, they had no representation, or if we want to generate language from the 3-dimensional models or point clouds directly. Our problem is that current methods really focus on synthetic data, which is usually noise-free, infinitely dense, for example, CAD models, which can be sampled infinitely, and they have no occlusions as we are aware of the whole geometry. And we will have real-world data on the other side, which is noisy, sparse, and occluded, which represents real life, but it's hard to collect and lacks diversity compared to synthetic data, which is diverse and easy to produce, but it's not representative of real use cases. So the problem is that current methods generalize poorly across these 2 domains simultaneously. Our method proposes a pipeline first. In this pipeline, assume we have real-world data set of LiDAR scans, multi-view RGB images, and 3D annotations. And given these, given the annotations, we can locate the objects and then crop those out from the LiDAR point cloud and then project those 2 images, getting the 3D and 2D representations. And then we can use a BLM on the 2D representation on the image and generate a description of it, thus requiring these image, text, and point cloud triplets. After this, we propose a method of combining synthetic and real-world triplets using curriculum-based dataset mixing. And during training, we have a frozen text and image encoder like CLIP, and then we want to train a 3D encoder. So this representation we trained is aligned, this feature is aligned in the CLIP space with the image and text representations. After that, once we have the trained model, we freeze the text and 3D encoders, and then given a vocabulary, we can use simultaneous ranking to classify each and every point cloud given its feature produced by the 3D encoder we just trained. As for results, the main results show that we bridge the synthetic and real gap efficiently. We improve zero-shot classification on new scenes and truck scenes, which are real-world autonomous driving datasets, while we stay competitive on the synthetic CAD model dataset of Observer's Elvis with over 1,000 classes. And we are also observe long-tail gains, where this curriculum mixing improves low-frequency classes without explicit reweighting during training. Our data is also, so we are also really data efficient, although we use these annotations during training, but we observe only a small percentage of real-world data is needed to produce a significant jump in accuracy on the real-world data set. For qualitative results, our method can retrieve fine-grained attributes of objects, such as a pedestrian is a police officer or is in a wheelchair, which might be useful for the system to modify its behavior during, for example, driving scenarios. And in the future, we could imagine pairing this with a class-agnostic 3D object detector with our method to obtain a granular semantic information of these object proposals. As such, for example, we have the truck, a car, we can even tell apart what kind of truck it is, if it's what kind of vehicle it is, what kind of pedestrian it is. Thank you for your attention, and our code and dataset is available at the following link on GitHub.